degree in civil engineering, where I focused in geotechnical engineering. Then I joined Black Veatch recently in August of 2020. And things I like to do on the side is support the local professional soccer team, Austin FC, in town, and go mountain biking. This is related to the theme of the presentation, but in this picture with the limestone bedrock is a cephalopod that had died out in the Cretaceous age, but is a nice imprint that I found while biking. So now I'm going to give a project overview of the CWIP segment 5-1 project. I was, again, a field engineer for Atkinson Construction who was hired to perform the work. This project is located in North San Antonio, Texas, and the owner is San Antonio Water Systems. The point of the project was to connect this terminus site where a water treatment plant and facility was being built to their existing infrastructure all the way down near Reach 4. Their system designer was Tetra Tech, the tunnel engineer was Subterra, and the geotechnical engineer was Arias Geoprofessionals. Black Veatch was actually the construction managers of the project, so I worked with some colleagues before joining their team. And then at the end of the day, a 54-inch steel water pipeline was installed within the multiple excavations that we had. And going a bit further into the project overview, I'll be focusing on Reach 1 tunnel, the majority of this presentation, but there was a lot of other components of this project. With Reach 1, it was about a 7.5-foot diameter Robbins double shield TBM going, the tunnel drive was about 0.9 miles, almost a mile. Reach 2 was a 1,500-foot excavation, 8 feet wide, performed by open cut, so the pipe was just laid in the ground in the street. Reach 3 was 102-inch diameter, which is about 8.5 feet. Heron Connect single shield TBM, and then there was a small section across a Texas Department of Transportation highway that involved hand mining. It was only about 500 feet. And this project was pretty unique because it had a really tight schedule constraint, which required 2 tunnel boring machines on the project to be utilized at the same time, versus it's typical for other projects to just have one TBM and then keep hopping to the next sections that need to be excavated. So what did the geology of the area look like within this project site? The Edwards Formation is a Cretaceous age limestone that consists of relatively soft to hard limestone. This limestone is typically described as vuggy, and it can have solution cavities and voids because it's in a karst area, and it can have layers of very hard chert, which is also known as, like, colloquially as flint. And then these voids are often infilled with red clay. So that's like a huge range of different types of ground conditions that you can have just within this one type of limestone. And but thankfully we are above the groundwater table. And limestone typically is formed when calcite precipitates out of the water containing dissolved calcium. And it's mentioning that, hey, this is Cretaceous age because that was the time when a majority of Texas and other parts of interior US were underwater. So what can karst features look like? This is a very extreme example of a karst feature. This is a picture of a local cavern within the San Antonio Hill Country area. There's a lot of caves and cavern systems that are open up to the public to just go and explore, like all the things that karst features can create. And there's about 1,300 caves, sinkholes, and springs known in Texas within the karst region. And karst is majority in limestone, and it is a type of terrain formed by the dissolution, aka the weathering of water-soluble rocks such as limestone, and it's generally characterized by sinkholes and caves. This figure was in the geotechnical baseline report, as well as the definition that I had mentioned, and it's showing the mapped karst features within the site area. You can see with my mouse, but it's also highlighted in these yellow and blue sections, is the tunnel alignment, and around the tunnel alignment are all the mapped karst features in these green dots. These features range from cavities to buggy rocks, observations, sinkholes, depression zones, and faults. And I believe like this area has only recently been developed within the last 30 years as San Antonio keeps expanding outwards. So a lot of these features are discovered during that new construction phase. So what did the geotechnical baseline report say about the rock core that they pulled up during the geotechnical investigation? And again, I'm focusing on Reach 1, which is what a majority of my photos are taken from further along in the presentation. But within Reach 1, we have a rock recovery from 0 to a max 100%, rock quality designation from minimum 0, max 100, and a rock mass rating from 25 to 89. Focusing mostly on the recovery and rock quality designation, these are like huge ranges, basically the biggest range that you can get about this rock. So we're saying that we can have no rock to 100% rock. It can be, and that rock can be up to 17,000 PSI. So what equipment did we select as a contractor to perform this work with pretty variable geology? We had to go with the most extreme example, which in this case is we needed to be able to excavate through the hard rock. So we used 2 road header machines to excavate the starter tunnel, which was about 200 feet, and it used these heads to advance forward. And then we used a Robbins double shield TBM to excavate the majority of the tunnel. Talking a little bit further about the TBM itself, I think some of these design components of the TBM are pretty important whenever you're picking out machinery to go through the ground. But you have the disc cutters on the cutter head that are cutting the rock it's meant to cut hard rock like a pizza cutter does, breaking through the ground. And then you have these blue stabilizer pads that are meant to stabilize the can of the TBM whenever this cutter head is rotating and advancing forward. And then we're also calling it a double shield. However, this kind of looks like a triple shield, but what we're saying is there's this front can and a tail can, and then this is an internal sliding shield, which then is not part of the double shield name. But we have all these shields in place so we can erect the initial ground support within the machine. So we're not so crew and men and guys who are building this aren't exposed to the ground that's right above them. And I like to point out the advantages of a double shield TBM is that it can move in 2 different capacities. It can use these gripper shields, which push out against the rock. The rock needs to be pretty strong to receive that pressure, but it can push out against the rock to help the machine contract and expand and advance the TBM forward, or it can push off the rock from the tail shield, and I'll show that on the next slide. So this is the second way that in this picture I'm showing the second way that this TBM can move forward. It's related to the ground support. We had steel sets and lagging on 5-foot intervals required throughout the entire length of the tunnel. And sometimes we did have to utilize this thrust ring. So that's the second way the TBM can move forward. This thrust ring can expand and push off the steel support within the ground to move the machine forward. You'll also notice throughout these photos, a lot of these steel support isn't really needed because the ground is pretty self-supporting. But there were some cases where we would hit clay even though we are in good rock where the ground support was previously being was currently being installed, so like 50 feet behind the TBM cutter head. So even though we had good ground that didn't really need the steel sets, but we still had to install them just in case, you know, we had to push the machine forward and use that capability. So what did we find while excavating the ground? We found the good rock, and these are all kind of in contractor terms. We found the good rock, which, you know, we could blow through pretty quickly. It was there was some really good shifts with while we were in this type of rock. And the picture on the left shows the circular pattern that the cutters are making in the ground to fracture that rock. I really like this picture because the TBM has backed up about 20 feet, and you can just really see what the machine is going through in the ground. You can also see these about 3 dark layers in the upper part of the tunnel, which are those horizontal chert layers. And chert can be extremely abrasive and about the same strength and abrasivity as quartz, which can cause the cutters to wear down much quicker on a TBM than in other types of rock. And so again, we need to have equipment that can account for that worst case scenario, that really, really hard and strong abrasive rock. But also we see in this photo that in the crown of the tunnel, is a vuggy feature, which is showing that the karst process of the dissolution of this rock has begun. So originally starting out as vuggy rock, transitioning to maybe having a void there, and then into potentially cavernous material. And again, this is just a picture of how like the steel sets are not really needed, but and the ground's pretty self-supported. We also hit the not so great rock. In this picture, we are beginning the construction of the starter tunnel, which is used to launch the TBM, and we've encountered a clay seam. So it's being supported by wire mesh and rock bolts. But this clay seam is something that was typical to encounter while excavating through this limestone. And again, this clay is formed by the weathering of the limestone. But you know, it causes dangerous conditions. You don't know how big this clay seam is, if it keeps expanding. I'm pretty sure we chased that layer like all the way through the starter tunnel, but it definitely is an area that needs to be well supported in order to work under it. And then we hit the really, really bad rock, also known as the shit rock in contractor terms. And maybe you don't even need to call it rock because it's basically just clay with some rock in it, and or can look like soup depending on how much water is added while tunneling. And this was like the worst stuff to go through because the TBM is not made to go through clay. We had what's interesting, I think, about this is with the volume of clay that we're seeing, you think like maybe that's how it was like naturally deposited, but again, this is still just a secondary. This is because of the secondary weathering, and it produces this type of insoluble material. Limestone consists of calcium carbonate, and that 90% of the rock is made of calcite, and around 5 to 10% can consist of quartz or clay minerals. So the weathering of carbonate rocks leads to these insoluble materials just building up in the voids, and some layers can have higher clay content, which can then produce these sections within limestone. So we also, this is along the theme of the really, really bad rock. I wanted to show this picture because this is one of the miners, Sam, in the TBM, and I did not take this picture. I know he's not wearing any PPE, but he's doing a pretty important job. Definitely the lowest man on the totem pole job, which is to remove kind of all of the clay that is building up, where that is then preventing the TBM from going forward. So crew members would have to like remove like all the clay within the cutter head, because the cutters are meant to deal with pretty strong competent rock, not clay. So anything that can spin is then getting stuck by the clay, clogging it up. And also, I put this picture of the TBM on the right again in here, because with this double shield design, this interior shield was it's meant to be there. However, it's not extending the shield all the way down to the bottom. And I'm sure that's part of the TBM design, but whenever we're going through hard rock, not a problem. But whenever we're going through these clayey sections, this bottom missing part of the shield would then act like a scraper and scrape up the bottom of the tunnel, with then bringing in clay into the TBM, and that's where all the hydraulic hoses are sitting, electrical cords, important pieces of the TBM, pumps, motors, stuff like that. So that's what this guy is doing in this picture, and like this would just delay tunnel excavation. So we also hit the rocks with voids. Again, the weathering process has begun within the limestone. It's no longer a bug. We're starting to see a lot more of that rock has been weathered away. We have in these pictures within the tunnel, there's these brackets that are installed for surveying equipment, and the surveying process would take so long just because in trying to level a bracket in areas where there was little to no rock just made things challenging. There had been other tunnels that our team had worked on that was in like very good rock. So you only needed tiny little 3/4 inch bolts, no problem to just zip up there and install the bracket, but this took a lot more time. Then we hit the blocky rock. This is one of my favorite pictures that one of the guys on underground took, but this is what's going on here. This is a picture of the shield of the TBM, so we're looking at the exterior as it's moving through the ground. This ground looks pretty different than like anything I had shown before in this presentation, and you can see that there's huge overbreak that has happened, and this could have been a potential fault zone. With this unit, maybe was a bit stronger and more brittle. So whenever that TBM is excavating through the ground, it's breaking, and it's just breaking how it wants to. It's breaking how it's jointed in this blocky manner. So this was very challenging to get through and to excavate through, because it was a circle going through a square. And I had mentioned before with this TBM, the double shield TBM, it can move in 2 different ways. And what we're seeing in this picture is we're looking at the gripper shield, and the gripper shield isn't really able to be utilized because there is so much overbreak. It couldn't really get a strong connection with the ground. So the secondary function, or like the second function, the TBM had to push off the ground support. And even that wasn't enough force to just kind of move this machine forward. And I believe additional hydraulic rams were just brought in to push the machine. Along this 1 mile long tunnel, we also hit rocks, and we found rocks with large karst features, aka we found a cave. And this was just a unique experience. I was pretty excited to see some ground that like no one had ever seen before, but it was a good thing that the TBM operator stopped before going any further. Where I'm standing, I'm about 5'3". The tunnel is about 7.5 feet, and then you can see just the void behind me is a lot bigger, pretty wide. But the TBM had made its mark in the ground, with the kind of showing like a semicircle shape, and then the void is to the left, and you can see the because of the weathering, it has also brought in a ton of clay. So we weren't really mining through much rock at all at this point, just clay in rock. And that was a unique challenge that we had to solve. So this is again another picture of the void that we encountered. At this point, the first picture I showed was when we first got in there and got a look at it. The second picture was after we had already placed concrete at the bottom of the void. There was no wildlife down there, no cave creatures, so we were able to kind of close it up as quickly as possible. And above the cavern, we could access it from the surface, which was also lucky. It wasn't in a roadway or anything like that. It was just in a field. So we mobilized the drill rig out there, dropped the hole into the ground, started drilling, and then, eventually started pumping concrete. While we were drilling, actually, you could just see sometimes the drill rig rod just dropped a few inches or a foot, again, to just show that, yeah, we're definitely in karstic ground. And the picture on the right is taken from the TBM, where you can enter into see on the other side of the TBM. So you can see the cutters on the exterior, and then the crews built a bulkhead to hold back that concrete. So yay, we finally made it that 1 mile, which is in theory not that long for a tunnel, but it really took some work to get through that ground. So it was an exciting day whenever we holed through. And then this is also on hole through day. I wanted to show a picture of the crew who put in a lot of work and a lot of hours trying to get that piece of steel, the TBM, through the ground. And this picture is interesting because here you have these horseshoe steel sets that were required by the contract documents to be installed. However, they're really not serving any purpose. And that just goes to show it's important for the contractor and designer to work together once the ground is opened. Otherwise, you kind of can get these basically skeleton versions of ground support. I believe the purpose of these steel sets long term was so that they could support the ground to reduce floating on the steel water pipe. But again, we're not even touching the ground. So next step was to install the pipe. But how are we going to install the pipe when our tunnel is looking a little crazy? Maybe it's looking, in some cases, like a roller coaster. And this was a problem that we knew before we finished the tunnel that we needed to solve. These pictures are during tunneling. The back of the machine, basically all the supporting equipment called the trailing gear, is veering to, on the left, this left picture, is veering to the hard left, which is not how it's supposed to be. And again, the right kind of the trailing gears kind of looks wonky. You can't see a straight line essentially as the picture goes further back. So we had to solve this problem because the ground in some cases did dictate where the TBM went. When it was going through that blocky ground, the ground was kind of the controlling factor, not necessarily the machine. And also when they hit kind of those sporadic clay sections, the TBM is going to veer down or up or wherever to those softer zones rather than the rock. So we decided, or we knew that we needed to remine, and this is not something that happens on many job sites at all. So it's unique experience to go through. In this picture on the right, we have the tunnel has expanded. It's gone from a circular ground support to horseshoes. It's gone a lot bigger as well. And again, this is through the blocky section where there was a lot of issues, but we had to open up the ground in order to fit those 40-foot pieces of pipe. We again, this is a picture of the blocky ground, and I'm 5'3". Tunnel was supposed to be 7.5 feet, and this is a lot bigger than that. And that was just to get the pipe on grade and within the specified alignment, and so we could fit and so we could just have be able to construct that pipe and string it together underground. So yay, the pipe fits. I took this picture while we were riding in with National Welding, who performed the pipe installation. You can see this ground is, again, an area that required like us to remine. It's not a very, it's a little blurry of a picture, but this was an area where the ground support was definitely in contact in the ground and supporting the ground, versus like it's just hard limestone. So, and you can also see like the pipe, which is like barely fitting on the left side through the tunnel. But we had to do this to not only to get the pipe through, but to get those minimum tolerances around the pipe whenever we were putting grout in. So after it was installed, it was welded by National Welding, and cellular grout was placed by Pigco. And going back to the original definition I provided that was in the geotechnical baseline report, going back to the original definition of the Edwards limestone, the Edwards Formation is a Cretaceous age limestone consisting of relatively soft to hard limestone. This limestone is typically described as buggy and can have solution cavities and voids, all of that which we've seen. We also saw layers of very hard chert, and that the voids were often infilled with red clay. So while this definition was like exactly spot on of everything that we had encountered just within that 1 mile stretch, it still makes it really like, and that's the known knowledge for the engineer, for the contractor, for the owner. It still made that excavation very challenging. So then after the project, it was time for me to relax and start UT grad school. I got to basically start the project and end it. It was perfect timing. And grad school started right after that in August of 2020. So I appreciate you guys for listening, and I would like to open it up to questions, and we can talk about some of the pictures. Thank you. I'm going to stop sharing for just a tad so I can see some faces.
Thanks, Audrey. That's an awesome presentation. Really love the pictures. I have a question, and we'll wait for the audience to type in as well, or we can chime in and ask questions just for everyone. Could you speak a little bit about the fault zone? I'm curious about the overcut that you mentioned over there, and what was the experience of whether any water inflow, what kind of softer material did you encounter?
Yeah, I'm not like, whenever I'd shown that picture to like one of our Black and Veatch geologists, and I was talking to him about like, why did it look like this? And he was the one who kind of put in my head that it was a potential fault zone, just because the rock looks so much different compared to what we typically were encountering with the limestone. I would have to go back and look at what they said about like the potential fault crossings to kind of like check if that aligned with where we were in the ground. But other than like with the potential fault zone, it was just blocky, like strong rock. And there was a tiny bit of water just throughout the whole tunnel, but like we were above the groundwater table, so there was no like big inflows, which I'm happy for, because we didn't need more weathering of the rock.
Right. Thank you. Luis?
Hey, yeah, Audrey, great presentation there. I've got a question for you. First of all, amazing photographs, and it's crazy to see that kind of live and in real time. I've worked on a few projects in sedimentary rock myself, and one of the things I was wondering is, did the engineers baseline any of the karst for this alignment in the geotechnical baseline report?
I think like they just said it wasn't, the geotechnical baseline report is about like, it's very small. So like I'm 90% sure, I have it opened up, but I'm pretty sure like they just said you're going to encounter karst, and then the way that they solved that was that there was like contingency money set aside. So like if the contractor did encounter something over 3 feet, then money was provided to the contractor to like fill it with the burlap, like the burlap bags and like filter fabric, like gravel, concrete, stuff like that.
Gotcha.
So yeah, so it wasn't super detailed, but so there wasn't like, oh, you're gonna expect 10% karst, 10% limestone. It wasn't broken down like that. It was just like, yeah, you're gonna hit this.
No, that makes sense. And karst is always one of those tricky things to kind of capture in these kinds of reports, right? How do you capture the unknown for a contractor to kind of quantify and put a number to? So that's interesting. Yeah.
So I think it was interesting the way they solved that problem too, just kind of having like a separate money bucket. But I guess like a question I have, maybe if you guys want to participate, is given like this information, would you have done anything different in design or construction? Would you have used a different type of machine or different type of ground support?
So in my experience, and maybe they did do this for this project, but I didn't hear or see you speak to it. But one thing that we try to do early on is geophysical work. So a lot of seismic refraction, kind of to get a better picture of what is down there. Now, geophysical methods, I caution because they're very interpretive. What one person sees, another person could say is something different. So you've always got to be very cautious about it. But when it comes to karst, that's typically kind of the first thing that people go to in order to address, well, what can we figure out is in here in addition to borings? Because nothing can beat the actual physical presence of getting a borehole, getting a rock core log and saying, yeah, we actually did encounter a void from here to here. So we can kind of do some ground truthing here as well.
Yeah. I think they did do a geophysical report, and it was very it was entertaining in a way, because like there were the colors associated with like the values that the report was providing. There was this one is a pink color, and this pink meant either absolutely no rock or very, very strong rock.
Right.
And we could point like after passing some areas that did have smaller voids, we could point exactly to the map and see that, but you don't know until you're there. And also along this section of tunnel is entertaining. Rumors get started and then they might get really blown up, but we had this again an area on the geophysical report called Big Blue, and like this is like we thought it was going to be like a ton of clay, and it was going to be like 500 feet of clay and all this stuff, just based off of that's the color it was associated with the ground we had previously been going through. And no, it was like perfectly fine. So maybe something had happened. Maybe there was like a geotextile or something that like caused an issues with the readings on the geophysical report. But yeah, so that did happen. It was just it was more helpful like after the fact.
Right. And then remind me again, oh no, go ahead, Rajat.
No, I was just going to say if there are more questions, you can post it in the chat as well.
I was just going to ask, was the TBM just a rock cutting phase TBM, or did it have, okay, so one thing that people try to do to kind of attack that, and it's also used in mixed phase conditions as well, is a hybrid EPB TBM. So it's like an EPB TBM with rock cutting phase capabilities. So it has the disc cutter capabilities to go through the rock, but it also does have the capabilities to shut and have a pressurized face in order to deal with that kind of karst environment.
Yeah.
Which is only good, which is good in soils, but once you hit that kind of cave system, then that's a different problem.
Yeah.
Entirely.
Hi there, my name is Anvesha. Unfortunately, I cannot turn on my video. I'm in a neck brace, so I'll pass on that. Question, since this was limestone, did you guys come across any of the issues with hazardous gases like methane or any of that?
Not on this project.
Okay.
Yeah, there's no like gassy environments.
And no significant groundwater infiltration either.
No, because we were above the groundwater table. Which might have been intentional, just because I'm not sure like why they picked this certain like alignment and depth, but yeah, it's that reduced lots of problems, but we're still, you know, the groundwater's still infiltrating in and dissolving that rock.
Yeah, that might have certainly, you know, one of the predominant factors to stay, you know, above the water table, because that certainly increases the risks that we take, right, with the groundwater infiltration and, you know, the kind of place you guys were in.
Mm-hmm.
Thanks for answering my question. Thanks.
No problem. Thanks.
Are there more questions? If not, I have a question for Audrey. Could you speak a little bit about what kind of toolware the TBM experienced and how many number of tool changes happened along the way?
Yes, you were asking questions that happened like 3 years ago, but I'll do my best. We did not have extensive toolware, like we did not have extensive toolware. The rock, like maybe we changed out like cutters like a handful of times, but like it was never a huge, like, you know, we needed to have backups on hand, but we didn't have like one designated person that was constantly attending to the cutters. I know in a different project in Atlanta that this Atkinson Construction also worked on, we had like a complete like little Connex box just set up to tend to fix the cutters. Yeah, so like the quartz or the flint like really didn't play like a huge factor into the wear.
Gotcha. Okay. Are there more questions? If not, we'll end the call and thank Audrey again for her time. Maybe it would be a little more valuable to chat with the students who are currently enrolled in undergraduate and graduate programs, because your experience is going to be quite significant for how they plan their careers ahead, in terms of first went to the project side and then you went to school.
Mm-hmm.
So in that sense, I think it's sort of a valuable experience that you can pass on.
Mm-hmm.
I'll try to arrange something with the students, obviously at the School of Mines, because I have good contacts over there, but along with it, even at Purdue. And if you can plan on connecting me with the students in UT Austin, even the ASCE groups or the Geo Institute groups are okay to connect with. I think this is a pretty unique case and there are many out there, but we don't know a lot about other engineers. But in your case, yeah, I think it's valuable to work on a tunnel project full time, gain experience, and then go back to grad school and probably get a better sense of what's being taught and can relate things better. So we'll try to arrange for something like that, and really appreciate you sharing your experience today.
Yeah, thank you. Yeah, I appreciate that. I was the like lost geology student senior year being like, maybe I should go get my master's in geology, and that didn't pan out. And I'm glad that it didn't, because I really like building tunnels, still has the geology, but once I worked, it provided more insight of what I wanted to do.
Awesome. Yeah, no, absolutely. If you plan on attending RETC later this year in Boston, I think it would be valuable for you to chat with the scholarship recipients and the students that arrive at the conference.
Okay.
Good, sorry, are you guys wrapping up? I apologize. I got a call that I had
Sure,
to
no.
jump on.
Please go ahead. Floor yours.
Yeah, just one question. Do you know why they went for this double shield with lagging? So I've seen designs with double shield grippers with lagging so that did they thrust off the lagging in
Yeah,
certain
like
locations?
in certain locations, and it honestly yes, in certain locations it was needed to thrust off because the face of the TBM is going through this clay section. So, or like they're in clay with wherever the grippers are. So they're needing to thrust off the ground support, but maybe that ground support is what doesn't have all of the lagging or whatever, because it looks pretty good whenever you're standing above it. So sometimes that like the steel sets within twist just because of that pressure that the pressure from the thrust ring. But I do think that it was needed to get through some of the sections because
sorry, the thrust ring, you dragged the thrust ring behind the TBM?
Well, it was in that tail shield, and so the rings are constantly being built in that tail shield and just being pushed out.
The steel sets are built.
Yeah.
Right, because there's no ring. It's just steel sets, right, and lagging behind the steel sets. So you're thrusting, but the jacks then thrusted directly against the steel sets.
Yes.
And was it only like a partial loading of the jacks thrusting against the steel sets, or like was it gripping and thrusting at the same time? Because the idea with a normal TBM is you have your thrust frame to begin, right, with the first couple of rings, and then after that you build up friction against the grout and against the total lining. So your lining is, the friction between the lining and the ground is technically taking up those thrust forces when you're deeper into it and when you're at the beginning is the thrust frame. Versus with a steel set, the only thing connecting one steel set to the next steel set is the lagging, right? And so you're not right? I mean, your lagging would buckle, right? And barely any friction with the steel set. So I'm just wondering kind of like, what's the idea behind the physics of how the steel set can actually assume the thrust loads?
I don't think I can speak to that, but I see what you're saying. I know that, I don't know like how much loading was actually on the steel sets.
No, it's cool. It's cool, but you saw them literally thrust against the steel sets, like put the jacks on the steel sets and push against the steel sets.
Like the ring pushes the as the machine moves forward, the ring pushes off. Maybe I'm wrong on that because now you're making me second guess. But like that's how it's basically operating how a single shield TBM would operate.
And sorry guys, you guys mind if I have some other questions? If somebody else wants some questions, this is just very interesting, kind of, because it's a weird TBM. It's kind of a weird TBM.
It's a different mechanism. Yeah. No, you're good.
So who designed the ground support for the TBM? Did Robbins come in and do the ground support together with Atkins Atkinson?
It was there's Tetra Tech or the Subterra Engineering.
Okay, yeah.
They were like his name was Chris Breeds. He was like the tunnel engineer, and then we worked with like SK Engineering to do the ground support. That's for like typical contractor. Like we typically used FK Engineering, but Robbins like wasn't that involved. And I don't know if I can like really speak to exactly what you're trying to get at, because now I'm like, is my memory skewed? But I do know that we pushed off the steel sets, and sometimes that force wasn't well taken, and so then things would like be twisted because there's like nothing, because everything like the lagging's like slightly longer than the other laggings, and like all the forces going into that one spot, and so there was issues moving the machine like that.
And sorry, guys, the last question, because I didn't see it, and I apologize that I had to step out and take a call here. But final lining, what was the final lining? Just cast in place?
No, it was the 54-inch steel water pipeline with grout.
Behind it, all right. So,
Mhm.
the extra dose of the pipeline was a little bit smaller than the intradose of the steel ribs, essentially.
Yeah.
Okay, no, it's so the reason that I'm coming at it is, as a tunnel engineer, this is steel ribs and lagging isn't something that I see in tunnel engineering very often, except for Robbins-like steel ribs and laggings, because they're coming from like old school mining people. And steel ribs and lagging is something in my experience that I've seen a lot, like old miners love steel ribs and laggings. But like if I'm designing a tunnel, it's much more rock bolts, mesh, and I'm sure Rajat can speak to this too, right? Like if you're doing ground support, it's rock bolts, mesh, shotcrete, or the lining. And
I think
the only other TBM that I've seen that has this type of support is also a weird double shield TBM that was put into place for an exploratory tunnel for a mine in Chile that also used for the worst support class steel ribs and lagging. So it's really interesting to see.
I think, okay, I can provide a bit more of reason of why, and I'm not a structural person, but like we had to use steel ribs and lagging because the contract documents made us. So that was part of my presentation, was like I said that the pipe, like for long-term support, they wanted those steel sets in place to take the load off load of the ground to then like better like to remove the load from the pipe. And I can't like speak to why that was the rule, but that was the rule. Like we even like tried to technically got approval to like put up rock bolts and mesh just behind the tail can because we didn't need it in all these cases. But like eventually steel sets had to go up, and that was to like protect the pipe. I just don't know, like I don't know how we would have gotten through the rock or like through the sections of clay if we didn't have like the thrusting function, because like how, I don't know, like just with maybe I'm like just with the clay sections, like a TBM hard rock TBM can't move through that very easily. So
yeah, no, I mean that's why I'm saying it's interesting. You know, how long was the first reach?
Just a mile, like, but it took like it took so long.
Yeah, and so I guess and it's not a high pressure, it's a sewage tunnel. It was, right?
Well, the water
was Black
pipeline
and Veatch the designer? Because if not, then I'll annoy some of the Black and Veatch guys in our group.
It was not.
Who was the designer? Was it WSP? Then I can annoy this WSP guy.
Tetra Tech was the designer.
Yeah, no, I'm just I suppose I'm surprised that it wasn't, you know, pipe jacking with some sort of like interim shaft or something like that to get over that, or just a regular TBM with cast in place lining that you then just use as the final lining instead of a steel lining.
But it was
it's
high
like,
pressured.
Sure. So it's a very uncommon design, is what I'm saying. And I work, but I have to say, I work primarily on larger infrastructure projects, also larger hydropower projects. And so it may just be kind of like because of the scale of the project, they were just like, let's just get in and do it down and dirty as we used to do it. It's chalk. Let's do this. It's very interesting.
Because like with the next project that San Antonio Water Systems did, it was a sewage pipeline. They used Hobos pipe. They were in soft ground, but they still used steel ribs and lagging, grouted the pipe in place. So it doesn't seem as.
Yeah, no, I mean, so we have a section of a CSO tunnel that we're working on right now that's also Hobos pipe, 8-foot diameter in hard rock, and but it's like in a 1,500 foot section, right? And the rest of the tunnel is not pressurized. So it's just always, because I've seen these types of designs before, I've never been involved in this type of design. It's always interesting to kind of see the designs and kind of it's unique in my experience. Yeah. And I don't know, Rajat or whatever, if you can speak to that too. It's unique in my experience. And I don't see too many of these. And that's why it's great to have an opportunity to chat with somebody like you. I apologize if it sounds like I'm like, why'd you do this?
Well, you're saying what's unique is that I use steel sets in hard rock, right?
Yeah, well, like, so steel sets in hard rock, also in my experience, come from like really old school mining tunnels. So like I was out inspecting the Eisenhower Johnson Memorial Tunnel in Colorado, which was built in the 70s. And that one is all steel sets, right? Hard rock steel sets and lagging. And then you kind of have, and then so my experience in tunneling has been kind of from the mining with the shotcrete and the rock bolts has swapped over from Europe sometime in like 80s, 90s to the US. And that's why, and since then, I don't see too much steel sets and lagging anymore. That steel sets and lagging is kind of like a 70s mining technique. I've seen people do it. I've just never had the opportunity to talk to anybody about it, really. You know, like,
yeah, but like you're saying in hard rock, right? Like that's the
yeah, in hard rock or I guess in soft rock.
Yeah, because in soils it's typical to use like steel ribs and lagging.
Yes.
You know, trenchless methods like that's kind of like almost a standard.
Yeah.
But in hard rock, it's not, like Vojta said, it's not as common.
Yeah. Well, so like I didn't present on this entire other section. The only other, we used the Herring Connect single shield TBM. Again, it's limestone. There were some voids. They had way less like interesting geological features encountered, but same project. So we're going through limestone. We're using a single shield TBM in hard rock, which I guess like, yeah, is pretty unique. And every push is requiring, like every push is off those steel sets. Like even when we were about to hole through, it's not like the machine could just take off and finish that last foot. No, we needed to build a steel set just because that's how the machine is going to move forward.
And is it lagging between the steel sets?
Yes.
Or just wood and lagging?
And like the tie rods. Yeah. So like, if you went into that tunnel, there's pictures where like multiple sets are like diagonal because of the force from the machine.
And the steel sets are they're bolted into the ground?
Well, they started to do that just to get some more like resistance
for the TBM. Yeah.
Yeah.
And the jack pads really go to the flange of the I-beams effectively and jack off of that flange portion of the I-beams or the web. I always forget if it's the web or the flange. I pay enough attention in structural engineering. You can tell I don't design many steel sets.
It's fine. Yes, that is my understanding.
And apropos, Luis, we don't do like any steel sets for design ever, like zero. Yeah, I mean we'll do like lattice girders for soft ground,
right,
just to maintain the shape, but like no I-beams ever.
Yeah, I was going to say lattice girders with shotcreting is what we have heard. This is pretty unique. I mean, we do a lot of steel rib and lagging for soft ground here in Midwest, but this is unheard of.
But like for example, steel rib and lagging, like Europeans for soft ground, like more with like pipe arch canopies or something like that, rather than steel rib and lagging. Like even steel rib and lagging is something for soft ground that I would never design.
Oh, wow.
Which isn't to say that it's not right. It's a different philosophy.
Right, it's just a different philosophy, right?
Yeah. So it's just interesting, right?
Yeah,
and your philosophy has to fit with the contractor. The contractor has to know to build what you're designing, and so on and so forth.
I would still be interested to see, like, I didn't get a chance to like dive deep in, but like why were those steel sets required. And they say it's because of like supporting, taking like to support the pipe in a long-term capacity, but we're
Yeah, no, it's very interesting. Interesting project. Sorry for jumping in late and like taking over everything, but like I had to ask.
It's all good. Thanks.
All right.
Yeah,
So
thanks,
we all,
guys.
I guess we all share that surprise of, thrusting off against those steel frames. And in some places, it kind of looked like in the horseshoe portion of the tunnel, the frames were just standing by themselves, no lagging between them.
Yeah.
Yeah, and like Abby's just writing, we're looking at steel sets and steel lagging for a small drill and blast roadheader tunnel in Poor Rock in Colorado. And like, yeah, you can do it. It's just a different philosophy, right? And talk about Colorado, the EJMT tunnel is like all steel sets and lagging, right? It's like a bunch of steel sets. You have, historically, from what I know too, sorry that I'm kind of going on this conversation, you have yeah, Matt, I'll talk to you at some point in time. Sorry, Matt was just like, I know some things. Anyways, I'll shut up.
What? Well, wait, like going back to Abby's comment, steel sets and steel lagging for a small drill and blast and roadheader tunnel, that's going to have a lot of will have overcut, and then it's hard to get that ground support that's pre-designed in certain shape to be in contact with the ground. No.
Yeah. Sorry, again, like, this is why I think this is a great platform, because you can have these conversations. Yeah.
No, it's nice. I didn't know that it was like unique. Like, yes, I thought that it was a little
unique,
silly.
It's unique to me. It's unique to me.
Okay, but it seems like there's a general consensus. But it seems, I knew it was silly that we're having these steel sets just in hard rock that weren't really doing much. But yeah, I didn't know a different perspective.
Nothing silly. Listen, if you got the project done and it was in budget, that's all you need as a civil engineer. None of our projects